So we recently completed a look at the various phases of matter and how they interconvert. We saw what a tremendous amount of energy it can take to liberate individual molecules from the intermolecular forces holding them to their neighbors, and how inventors like Cullen were able to exploit that fact to design prototypical refrigeration systems. But there's so much more to the behavior of matter than just phase changes. Each phase of matter can be studied and used in and of itself. So now we embark on a new subset of lectures, a set in which we're going to give each of the three phases of matter individual attention. We'll concern ourselves not with how they interconvert, but how they behave in response to changes in conditions like temperature, pressure, expansion, and other stresses. Our discussion will begin with gases. Gases are tremendously versatile materials. We're constantly living under their influence, like the Earth's atmosphere, which is currently not only providing you with the oxygen you need to breathe, but transmitting heat from one region of the Earth to the other, creating wind for transportation, even protecting us from the more harmful rays of the sun, like the way that ozone absorbs damaging UV. Gases are also serving mankind in a broad array of engineered devices. The modern vapor compression system in your refrigerator at home, the pneumatic tools used to build that home, the air in your car tires, they all rely on gases to operate correctly. Not only that, but each of these devices relies on different gases and their responses to different conditions to get the job done. As diverse as these applications may seem, they all really rely on just a few time-tested rules which we can generally apply to all gases. We collectively call these rules gas laws. And understanding them is critical to appreciating what a remarkably versatile but predictable medium gases can be. To begin our discussion of gas laws in general, let's take a moment and catalog all of the critical properties of gases that can change in different situations. Of course, there are many properties we could consider, but since this is our first foray into the topic, let's focus on the most fundamental and important properties. The main properties include pressure, which is the amount of force that a gas exerts on the walls of its container. Next is volume, or how much space a gas occupies. We also need to consider the temperature of a gas, which is a measure of the amount of kinetic energy that its molecules possess. And finally, the most elementary property of a gas sample would be how many molecules make it up. We report this, of course, as the number of moles. As disparate as these properties may seem, pressure, volume, temperature, and amount, the truth is that they are all very closely related to one another, and their relationships constitute some of the most fundamental laws and theories of chemistry. Without understanding these relationships, many of the most critical and widely used engineering designs of our time would never have even been created. The long road to a law unifying the basic properties of gases begins with the Anglo-Irish philosopher, theologian, and chemist Robert Boyle. Son of a British earl, Robert Boyle was afforded great opportunity and education for a man living in the 17th century. Although he was a productive publisher in the fields of philosophy and theology, Boyle's greatest contributions to Western thought were almost certainly his work in the fledgling field of chemistry. Boyle's law, most simply stated mathematically, is this: pressure is proportional to the reciprocal of volume. But what does that really mean? Well, what that means is that if I have two identical samples of gas, as I do here, gas 1 and 2, and I apply pressure to one of them, increasing it, I expect the volume to decrease a proportional amount. Right? So an example of that would be what I've drawn down here. That in this case, because I have doubled the pressure, right, so P1 times 2, I must therefore have halved the volume, all other things considered equal. Now let me show you another equality, one that's a little bit obvious. P2 times V2 equals P2 times V2. I think we can all agree on that. That's pretty much indisputable. However, what Boyle's law allows me to do is create these equalities up here, which can then be substituted into one side of my equation down here. So I'll put my 0.5 V1 in place of V2. I'm going to put my 2 P1 in place of P2. And now I can see what happens here is that those two modifiers cancel. The 2 and the 1/2 when multiplied are going to multiply out to 1, canceling one another, leading me to this equality, which is very useful. P1V1 equals P2V2. So for any ideal gas whatsoever, all other things considered equal, that means number of moles, temperature, etc., the pressure times the volume must be equal to a constant. And this is the mathematical essence of Boyle's law. I'll make you a bet. I'll bet you that I can inflate this balloon fully with just one breath. What do you think? I'm going to just assume that you took the bet. Here we go. There's a catch, right? Davis always has a catch. First, that one breath. That should do it. I think I put myself at a disadvantage, right? Well, the catch, once I tie my balloon off here, is that I said I would only use one breath, but I didn't say I wouldn't use anything else. And what I'm going to use to win my bet with you is what's called a bell jar and Boyle's law. Now, a bell jar is just a jar here that I'm going to invert and put on a base here and seal with some vacuum grease so that I can evacuate it. In other words, I can lower the pressure inside the jar. And when I do that, we're going to observe the effects on the volume of this balloon, and then I'm going to collect my winnings from our bet. Here we go. Take a piece of tape here and secure this to the inside of the jar, just to be sure that it doesn't fall to the bottom and block the valve that's going to be removing the air. Okay. There we go. And just to be absolutely sure, I'll actually use a second piece. Here we go. Okay, that should stay put. All right, now I need to make my chamber that I'm going to use to generate the vacuum. So I'll invert the bell jar, placing it on the base, and I'll give it a little turn just to be sure that that grease on the bottom forms a nice airtight seal. And finally, of course, I've got to close it off completely, which means I've got to place a stopper in the top. There we go. Now, the only way that air can get in or out of this jar is through this hose on the side, which is attached to a vacuum pump. So it's time to finish inflating my balloon using Boyle's law. As the vacuum pump begins to run, the pressure inside of the bell jar is decreasing. And you should notice that as that happens, the volume of the balloon inside is increasing. Right? So as pressure decreases, volume increases. And if I wait long enough, my balloon will really start to inflate now. All right, I think it's fairly undeniable. I'm going to close the valve here to seal my chamber. Turn off my vacuum pump. What do you think? Looks like I've won. How did I win? I won because I knew that pressure and volume are inversely proportional to one another. And by reducing the pressure inside of my bell jar, I increased the volume of the gas contained inside of the balloon. And of course, Boyle's law works both ways, which means that if I let the pressure inside of this bell jar increase and go back to regular atmospheric pressure, I should see a corresponding change in the volume of the gas inside, right? Letting the pressure go back up, of course, means the volume of my balloon goes down. So our demonstration showed just what Boyle had demonstrated, that at fixed temperature, the pressure of a gas sample is inversely proportional to the volume that it occupies. This mathematical relationship is the first key to understanding the behavior of gases. But there's more to our quest to formulate a comprehensive description of how gases behave. The next piece of the puzzle begins with French physicist Guillaume Amontons. He was the first to make a comparison between the temperature and pressure of gaseous systems. Amontons was working in the early 1600s, and without the type of precise instrumentation that would be necessary to fully nail down the relationship between these two properties, what he did realize was that when a sample of gas in a fixed volume was cooled from the boiling point of water to the freezing point of water, the pressure always decreased by about 1/3, no matter what the gas. Unfortunately for Amontons, lack of appropriate instrumentation made testing his theories very difficult. It would take another century until another Frenchman by the name of Joseph-Louis Gay-Lussac would publish measurements reliable enough to establish a scientific law. So the fame largely goes to Gay-Lussac, though you may hear the term Amundsen's law also used to describe this relationship. Okay, let's take a look at Gay-Lussac's law using the same type of arrangement we have previously with our others. Gay-Lussac's law tells us that pressure and temperature must be proportional when all of the things are held constant. In other words, if I were to increase the temperature of this sample here by a factor of 2, I expect the pressure of it to increase by a factor of 2. Mathematically, we can pull the same tricks that we've been doing with all of the other laws that are governing ideal gases. And that is that we can create a substitution into our very simple equality here that allows us to get a relationship between the pressure and temperature of any two ideal gases that we choose. Because these 2's cancel, I end up with P1 over T1 equals P2 over T2. This, again, is a very common way to represent Gay-Lussac's law. Any of us who are motorists have experienced Gay-Lussac's law, especially if you live in an area with seasonal climates. If you do, you've almost certainly noticed that your car tires always seem to need a little bit of air put into them when the winter months come. This is Gay-Lussac's law in action. As the ambient temperature drops, the pressure of gas contained in your tires also drops, causing that little light on the dashboard to activate on the coldest days of the year, even when your tire doesn't have a leak. On to the third relationship that we need to examine. This one is between temperature and volume. We already know from the work of Amundsen's and Gay-Lussac that heating gases at constant volume increases the pressure that they exert. But what if we interchange the roles of pressure and volume? What if instead we heat or cool a sample of gas under constant pressure? The answer to this question came from the work of Jacques Charles, yet another French investigator from the 18th century, and also one of the West's first ever balloonists. Although there's evidence that East Asian cultures may have mastered the technology of balloon flight centuries earlier, the science of using heated gases to generate lift really took off, so to speak, in 1780s France. So, Charles was heating gases and observing them just like Amundsen and Gay-Lussac, but the key difference is that his system, a balloon, did not maintain a fixed volume. The walls of his balloons could expand, changing their volume in response to temperature. Charles famously tested a number of gases as potential fillers for hot air balloons, and he noted something curious during his testing. He noticed that regardless of which gas he used, his test balloons always expanded by the same amount when heated to the same extent. This remarkable result became the inspiration for Charles' law, which states that when pressure is held constant, a sample of gas will increase in volume proportionally to its absolute temperature. If we look at Charles' law the same way that we've been looking at the others, we see that temperature is proportional to volume according to Charles' law. So, keeping all other things constant, I expect to see this relationship. So if we give it the same treatment as before, let's increase the temperature of an identical sample. You notice that when I did that, the volume increased. And if I'm looking at my temperature in absolute temperature units like kelvins, T2 must be equal to 2.0 T1 if I doubled the temperature. And Charles' law tells me that that means that my new volume is going to be 2 times that of V1. So, putting that into yet another very simple equality, we can arrive at a mathematical arrangement that lets us see Charles' law in action. The 2's cancel in this case when I put temperature over volume, and so here we have again an equation that allows us to relate the temperature and volume of any sample when all other things are held constant. This is Charles' law. So Charles' law has clear applications in aviation, explaining and predicting how heating the air inside of a balloon causes it to expand and become buoyant in the atmosphere. But it can also help us solve more everyday problems. Anyone who enjoys a nice game of ping pong now and then has probably found themselves in a situation like this once in a while. A dented ping pong ball. Now, this presents a real problem if you want to continue play and let's say that's your last ping pong ball. But with a little bit of chemical knowledge, we can fix this problem. Let's think about how. Now, in order to save this ping pong ball, I have to apply a force from the inside pushing out to get that dent to come out. But of course, that's not going to lend itself very well to me doing anything with my hands because I can't get my hand inside of the ping pong ball. But what is inside of the ping pong ball? Air. And that trapped air is a gas, actually a mixture of gases that will follow Charles' law. Charles' law tells me if I heat the ping pong ball sufficiently, the volume of the gas inside will increase. In other words, it will begin to expand, and in doing so, apply a force to this ping pong ball from the inside out, saving it and fixing the dent. So I've got a little bit of boiling water here, and I'm actually going to try this right now. I'll put on some safety glasses here just to be very, very careful. And I'm going to place my ping pong ball into the boiling water. And I'll just give it a little agitation. I'll spin it around a bit to try to avoid it from getting too hot on any one side. And in very, very short amount of time, you can see that the dent has been removed from my ping pong ball. All because of Charles' law predicting that the gas inside will expand in response to an increase in temperature. That's a pretty neat trick, right? But the usefulness of Charles' law goes far beyond just saving dented ping pong balls. Turn the relationship on its head and think about what might happen if you were to cause a gas to expand under constant conditions. According to Charles' law, the temperature of that gas should proportionally drop, causing the release of heat. Now, if we were to compress that vapor again somewhat, the temperature of the sample should rise, absorbing heat. You can probably see where I'm going with this, can't you? Right, Charles' law explains modern refrigeration systems. Just like Cullen's system, a refrigerant absorbs heat in a cooling compartment, then releases it in a separate region of the device. But modern refrigerators, sometimes called vapor compression systems, don't rely on the heat of vaporization like Cullen's did, but rather keep the refrigerant in the gas phase, simply compressing and decompressing the gas as it flows into and out of the cooling region of the refrigerator. Our final gas law of the lecture is known as Avogadro's law. We've already met Amedeo Avogadro, the Italian chemist whose name is attached to the mole. But Avogadro's fame doesn't stop there. He's also known for a famous law which he published in 1811, shortly after Gay-Lussac's law had gained acceptance. Avogadro noticed that at fixed conditions of volume, temperature, and pressure, samples of gases always seemed to have a mass which was proportional to the molecular or atomic mass of the gas. So essentially, Avogadro's law states that under constant conditions of pressure and temperature, an equal volume of gas would contain an equal number of particles. Now from this we can infer a more useful relationship which is more commonly presented as Avogadro's law now. And that is the proportionality of the number of atoms or molecules to the volume that they occupy in the gas phase. The simplest way to state Avogadro's law mathematically would be this. The volume of a sample is proportional to the number of moles in that sample, all other things considered equal. So at the same pressures and the same temperatures, we can always expect the volume and the number of moles to be proportional. In other words, let's say I have two identical samples, and I'm going to double the number of moles in my sample here on the right. In order to maintain constant pressure, that volume is going to have to expand by a factor of 2. So N2 equals 2 times N1, and V2 equals 2 times V1. Now, just as before, let me show you an equality that we can all agree on. N2 over V2 equals N2 over V2. That's indisputable. But again, using Avogadro's observations, I can insert these 2.0 N1 and 2.0 V1s into one side of the equation and get a more useful equality that isn't quite so obvious. In this case, my 2's cancel, and I can determine that N1 over V1 equals N2 over V2. So, under conditions of constant pressure and temperature, Avogadro's law gives me a ratio, proportionality, for any ideal gas whatsoever. N1 over V1 is always equal to N2 over V2. Avogadro's law is the principle that underpins technologies like pneumatic pistons. A typical pneumatic piston design relies on the introduction of gas from a pressurized container into a sealed compartment within the piston. As the number of gas molecules inside the piston increases, its volume must also increase. It's this expansion that the piston turns into motion, tapping the process to create usable energy. Another great example of Avogadro's law is breathing. Your body has muscles which it can use to expand your lungs. And when the volume increases under the constant pressure of our atmosphere, atmospheric gases, including essential oxygen, rush into your lungs in accordance with Avogadro's law. When it's time to exhale, decreasing the volume of your lungs causes your body to expel unwanted and potentially toxic carbon dioxide. So we just finished reviewing just over 100 years of experimentation with gases and their most fundamental properties. We've seen how some of the founding fathers of chemistry used the scientific method, holding certain conditions constant while altering others, and then observing the effects. And this led to the understanding of relations between pressure and volume in the form of Boyle's law, temperature and pressure as Gay-Lussac's law, temperature and volume in the form of Charles' law, and the mole count to the volume in the form of Avogadro's law. But at some time during our discussion, you might have asked yourself, can't all of these values change in natural systems? Nature doesn't do us the favor of changing just one variable at a time. Natural systems are complex and often undergo changes in temperature, volume, pressure, and quantity all in a single process. So what do we do now? We turn to mathematics, and we realize that if each of these relationships is independently true, then we should be able to combine them into a single equation, which will describe how they might all change in concert as a more complex process takes place. The combined gas law is the first of our gas laws to exploit some similarities among all of the other gas laws that we've looked at so far, specifically Boyle's law, Charles' law, and Gay-Lussac's law. Now, let's think about this. Boyle's law is pressure proportional to 1 over volume. Charles' volume is proportional to temperature, and Gay-Lussac tells us that pressure is proportional to temperature. So we came up with new ways to express them in our previous discussions here, and I put those on this slide as well. But I'd like to call your attention to something interesting. Notice that in all of these representations, pressure and volume are in the numerators of the expressions. And in all of these, temperature is in the denominator of the expressions. So these have a commonality to them that we can exploit to create a gas law that encompasses them all. We simply combine them so that we have P1V1 over T1 equals P2V2 over T2. So pressure, volume, and temperature are all interrelated, and changing any one or all three of them should have effects that we can predict using what we call the combined gas law. And if I want to get my original laws back, I can simply take my combined gas law, for example, in the case of Boyle's law, assume I hold temperature constant, which we have to do for Boyle's law to be true. Well, that means T1 equals T2. They cancel. Here we are at Boyle's law. What about Charles' law? Volume and temperature. This relationship is only true when pressure is constant. Therefore, P1 and P2 must be equal. Cancel them out. We get Charles' law. Gay-Lussac's law, pressure and temperature. Only true if we hold volume constant. Therefore, volume should cancel. And here we go. We have Gay-Lussac's law again. So the combined gas law is nice because it's a total representation of how all three of these laws interplay with one another and allows us to model even more complex systems where not just one, but sometimes two variables are changing. The ideal gas law is the king of all the gas laws. In this case, we get Avogadro back into the equation. Remember, we left him out last time during the combined gas law derivation. But now we're going to use Avogadro's law and similar logic to create this universal equation that has so many uses in chemistry. Again, here are our relationships that are defined by all of them, including Avogadro's volume proportional to the number of moles. If I put our derived equations up, comparing two systems, we can do the same kind of analysis as previously. Notice that, again, pressure and volume are always in the numerator, and that along with temperature in the denominator, Avogadro's law allows us to place number of moles. So that means we can combine all of these into one gigantic gas law the same way that we did with combined gas law, this time including number of moles. P1 V1 over N1 T1 equals P2 V2 over N2 T2. This is essentially the ideal gas law, but we're used to seeing it written a little bit differently. So let's take that ideal gas law and break it down a little bit more. If PV over NT always equals PV over NT, then those terms must be constant. And we call that constant value R, the ideal gas constant. So let's take our equation here and acknowledge that both of these are equal to the same value, R. Well, if that's true, then I can rearrange these equations for any single gas. PV equals nRT, a much more common version of the ideal gas law, all based in the same mathematics and the same relationships as the other version that I showed you previously. So this is the source of the famous PV equals nRT equation. This equation, which took a century to construct, allows us to predict any of the 4 variables that it contains under any conditions that we may need. It's time to sum up for this lecture. In this lecture, we concerned ourselves with some of the most basic laws describing the behavior of gases. We looked at Boyle's law, which describes the relationship between the pressure and the volume of a gas. We mentioned Gay-Lussac's law, which reports on temperature-pressure relationships. Then we talked about Charles' law, which relates temperature to volume. And finally, we talked about Avogadro's law, which established proportionality between the volume and the number of moles of a gas. Next, we combined these laws into larger mathematical operations that can account for situations in which not just one, but some or even all of these 4 properties are changing, giving us a powerful tool for use in engineering and design. So gases behave predictably, quite predictably. But why? We haven't yet peeled back the layers and asked that all-important question, what is it about how gases behave at the molecular and atomic level that makes them act so ideally? The answer can be summed up in 3 words: kinetic molecular theory, the topic of our next lecture on the chemistry of gases.